All right, so this is your next video. We've been talking about the universe and we've been learning lots about it, and several of you had questions last week, and your big major question is, well, how do we know all of this? And that's where this week's lesson is going to come into play. This week's video is called Waves. Well, what exactly is a wave? A wave is a transfer of energy. That's all it is a transfer of energy. So I've given you some examples: water waves, a stadium wave, the slinky wave, light waves, and radio waves. It's just simply a transfer of energy from a particular source. So for the water waves, the source might be the gravitational pull of the moon creating the tides. For the stadium wave, the source would be the individual people. Now, the type of wave is determined how the energy actually interacts with the matter. So we've got two types of waves. We have mechanical waves and we have electromagnetic waves. Mechanical waves require matter, and we call that matter a medium. So if you can remember M, and M, all of that together, mechanical waves, they have to have matter to travel. Basically, in a mechanical wave, the energy is going to come in contact with the individual particles, and it's going to vibrate those particles, and the vibration is what we actually see if it's an example like a slinky wave. A water wave, the same deal. If you were to follow a droplet of water, that water droplet is not ever going to get close to shore. The energy itself gets close to shore, but that water droplet in the middle of the ocean is going to stay there. Just like you in a stadium are going to go up and down in your seat, you don't move along with the wave, you just simply stay there and you quote unquote vibrate. Well, the other type of wave doesn't require matter to travel, which means it can travel in space, and we'll get to that in just a moment. It has electrical and magnetic properties, which is why we call it an electromagnetic wave. And I've given you some examples: radio waves, microwaves, infrared or heat waves, and then visible light waves, ultraviolet, X-ray, and gamma. Now, all mechanical waves have properties, and I've given you a drawing here. You see that the black line is called a resting position. This is where the particles are always going to return to before they move in the other direction. Now, the distance that the particles travel from that resting position upward or resting position downward is called the amplitude, and you'll get to see a variety of amplitudes as we go through. Now, what is that top point called? Well, it's called a crest. So the crest of the wave, if you do any surfing or follow any surfers, you know that that's where somebody surfs, is the crest of the wave. Likewise, the opposite portion, the downward part, is called a trough. So it's constantly going between crest, resting position, trough, resting position, and crest. Now, when we measure from crest to crest or from trough to trough, we call that the wavelength, and that's how we can measure the distance of the wave. So electromagnetic waves are going to have these same properties, but a couple of other things I wanted to add. All of our electromagnetic waves travel at the same speed, which is 300,000 kilometers per second. The amount of energy for each one of our electromagnetic waves is directly related to how big that wave is, so from crest to crest or trough to trough, and how many waves are going to come through, which is what we call the frequency. So less energy means that the wavelength is going to be stretched out, those waves are going to be longer, and they're going to be lower frequency. More energy is going to mean that the wave is shorter, and we're going to have a higher frequency. More of them can come through. And since the EM waves don't need a medium or matter to travel, they can travel through the vacuum of space, which is why we're talking about it right now. The EM waves are all ordered in a specific order called the electromagnetic spectrum. I would like for you to pause the video at this point and go ahead and sketch this graphic in your notes. You'll notice on here that I've put them in a particular order, starting with radio, then microwave, infrared, visible light, ultraviolet, X-ray, and gamma. And I've given you the trend of the spectrum. On the left side of the spectrum, it's low frequency, low energy, very long wavelength. And then on the right side, high frequency, high energy, and short wavelength. Now, this week's all about seeing these EM waves and telling us exactly what we get and how we get that information for space. And that's a wrap.